So our next speaker is Varan. I should have checked this in the last. Kola Gunter.
Yeah, you go.
Koyala Gunter from Tenstorrent, where he's a design verification engineer with more than 10 years experience in the CPU space. He has a passion for leveraging new technologies to speed up the verification process from pre-silicon to production. The title of his talk is Accelerating RISC-V Testbench Development with Open Source RISC-V RTL and Emulation.
You guys hear me? Thanks for the introduction. And this is a nice ordering of the presentation since we actually use some of the open hardware groups components in this presentation. So cool. So yeah, I'm at Tenstorrent, and what we're trying to do is develop a high-performance RISC-V core from the ground up. And we just started doing this a couple of years ago, and that includes DV along with RTL from scratch. It also includes DV from scratch, but no one wants to reinvent the wheel, right? Like, so I'll go into this more, but we want to use open source as much as possible. But early on, we also recognize emulation is key to our effort of bringing this core to life. And the question comes up is when you start DV and RTL from day zero, how do you keep DV at a critical path? You don't want your core to be able to start fetching instructions before you can verify anything. You've already lost a lot of time there. So I'll go into a little bit about what a typical verification cycle might look like on emulation and how we were able to speed that up. By the way, stop me anytime if you have any questions, I think. So this is what something might look like that you might be familiar with is, if you're working on a CPU core, a typical milestone is like booting an operating system on it. And, RTL development starts, then your test bench development starts a little bit after, now that you have RTL, that's more than a few lines of code. Then, you start thinking about emulation. How do I compile this for the emulator? And then what am I going to run on this emulator? And eventually you get to the point of the actual, maybe interesting point is where you can actually run the thing. And then, you find bugs there, you work through those, right? So this can be a months to year-long process. So what we want to do is shift left as much as possible by leveraging what's already out there. So RISC-V is a rich ecosystem. The Open Hardware Group has a ton of components. So we can, again, reuse VIP and also build around free RTL IP. So we don't need to wait for our core to work to start developing a test bench around it, right? So we can work around, and in our case, we use the CVA6 core that I mentioned earlier, and build a test bench around that. And then when our core is ready, just plug and play, mix and match. They're both RISC-V cores. So so that enabled us to start a bit earlier. When our start test bench development, actually even before RTL development, when RTL was still we could even start test bench development in the architectural phase, along with Linux and emulation bring up happening around the same time. Because the RTL was ready, you might as well start compiling it for the emulator. So here are some of the open source components we were able to use. Again, the CVA6 core. Then we used an open source instruction set simulator called Whisper to verify the CVA6 core against. And there's a protocol called the RVFI. That's an open protocol. The CVA6 and other cores support. That's an instruction trace format that allows us to to check against our golden model instruction set simulator. So basically, we have a DUT that has two things coming out of it: an AXI port to memory and an RVFI instruction trace. And as long as our DUT supports those two things, the test bench can work with it. So you can mix and match any DUT that has those two protocols. And we're sort of working on developing more transactors as well, along with AXI. So I think I can skip this because this is already done in the previous presentation. But the one thing I'd like to highlight is the CVA6 is a smaller core than the core we're developing. And so that allows us really fast test bench iteration time, especially when doing emulation on FPGAs, which can have like, you know, on the order of a half day, like 12-hour compiles. If you have something smaller that'll behave the same for free, that'll compile only in less than an hour, that allows your DV to iterate a lot faster, you know, 1 iteration a day versus like 8 iterations a day. So that was a big side effect or good benefit of using CVA6. Yeah. So we actually open sourced a prior version of this, but we haven't open sourced the current version. That's still being pipe cleaned right now. But this is a high level block diagram of the of our test bench. You can see the DUT up there. Again, that can be whatever you want it to be. These are the transactors we support. And I guess one thing to note that this is a little bit different from the core V that was mentioned in the previous presentation. This is not UVM based because UVM is not the most friendly for emulation. So this is more synthesizable Verilog and C++ based. And so we have a few transactors coming out of it, along with some device models at the very bottom that you might need for you know, booting Linux, like you need some sort of memory model, possibly like DRAM, and maybe address. And then we have a way to against the Whisper golden model. I don't want to delve in too much into our test bench and how it works, but these are a few high-level details. It's you know, and for emulation, speed is very important. You don't want your test bench to be the bottleneck, and that can take a lot of care and thought to do well. And that's honestly still a work in progress for us. You know, you had to understand how data transfer can be a bottleneck, and data processing time on your software can be a bottleneck versus VCS. It doesn't matter as much because VCS is taking up a lot of time. You also want to, for those familiar with emulation, the initial load time onto the emulator can take on the order of minutes. So you don't want to do that every time you start a new test. So this test bench also has the ability of sort of jamming, starting a new test without having to start from clock 0 again on the emulator. I guess, yeah. And it really depends on the size of the model. For bigger models, you can save up to 10 minutes doing this. This is just an example code of how the hardware and software talk to each other. Again, I won't go into too much of the details, but we leverage a lot of generation so we don't repeat ourselves. So this is a way to, we specify the RVFI packet, which is an instruction trace. This generates up is automatically, or the glue is all automatically generated for us. This allows us to be flexible in how we send packets across or abstract it away, because there's a lot of error-prone code if you do it by hand. This is C++ code that works with that packet. One thing I like to highlight is we want to make our components as reusable as possible to be in a library. And that means in a sense, no one component knows about any other component. There's no knowledge of a master or orchestrator that's bringing up all these components. It allows us to really mix and match. You can have a component and it's all specified in one file, and it has to know nothing about any other components, and no other component really has to have any knowledge of it. Yeah. So here's some numbers from this methodology. So like I said, our compile times while we're in the early bring up phases was reduced from 12 hours to 1 hour. That's a result of the number of LUTs being much, much smaller. We were able to find a prefetch finding a bunch of issues. Emulator tools usually don't work out of the box like simulator tools might. So we were able to find all these constructs, some at compile time, some at run time, that don't work so well. Testbench issues that weren't found in simulation, maybe simply the fact that you're running more cycles on emulation, or because of the asynchronous nature of emulation, it's just hard to find these bugs in simulation. We did find some Verilog issues that were in CVA6 that we filed as well, and then we're able to bring up Linux, and so on CVA6 or on our custom core, actually, we're able to boot Linux in less than 5 minutes, and that's with full instruction checking. So every instruction that our core is executing, checking against the golden model. This allows us to really debug very quickly compared to some emulation platforms that have. Yeah. So we booted Linux on CVA6 about 4 months before we did it on our custom core. So that's 4 months of saved DV development time. Yeah. And yeah, that's all I had. Anyone have any questions?
Again,
Great presentation, by the way. One question. Are you going to submit that CVA6 bug to the CVA6 repository?
Oh yeah, so I should be more transparent. So the testbench tracing bug, we did submit a PR on CVA6. The RTL bug, maybe I should have put bug in quotes. It was a speculative access to an address we didn't expect it to fetch from. So in some ways, that's you could consider that a bug to be something outside the core, like it should be squashing that. So we didn't. I don't know. We didn't really file that one. Yeah.
Okay. Don't be shy about creating an issue about anything, because if it's not a bug in the RTL, that's fine. But we would rather respond to a non-bug than miss one.
Yeah, of course.
Thank you very much.
Okay. Any more questions in the audience? Otherwise, we'll go to the online questions. Okay, so the first online question is, does your test plan cover cache memory coherency?
Yeah. Yes. I guess it's probably an open-ended question. I'll be going into more. So this test bench diagram I drew here is almost like, I'm not going to say black box, but maybe gray box testing, where we're only testing the instruction traces coming out. We do have, for RDUT, more white box testing done inside that I'm not including as part of the test bench here, but this framework allows you to add custom checkers like that pretty easily and integrate it into the test bench. So if you have a new checker that checks something very specific to your core, you can add it. I will add though, so the Whisper, which again is available on github.com under the Tenstorrent group, has a pretty cool checker called a memory consistency model checker. I'm not aware of any other, at least open source, checkers of the RV, the RISC-V weak memory ordering spec. And we extended the RVFI, the RVFI specification to add some more information to be able to talk to the Whisper MCM checker to do those checks as well.
Okay. And is this documented? Somebody's asking, is there a bit more detail of all the various blocks and processes and units for the actual test bench architecture?
Yeah, sorry, externally, we don't have much of this available yet. That is in the plan. I'm not sure the exact timeline, but at that point we would document it well,
Okay.
hopefully.
And it says to be open sourced, and do you have a date or?
So we open sourced like a primitive version of it a couple of years ago. And then this is like version 2.0. So and we haven't released this version yet. Yeah. And sorry, no exact date that I can commit to right now. Yeah.
Okay, months away, weeks away, years away?
Months away.
Months away.
Yeah.
Okay. Okay. Right. Okay. If there's no more questions in the audience, that's all the online questions. So we'll say thank you very much, Learn. Thank you.